In this section, we're going to be talking about sectors. Sectors are basically portions of circles or pieces that we can extract out, almost like a slice of cake, a slice of pie, or, of course, since we're in New York City, a slice of pizza. Sectors is just basically that. What we're going to be working with today is going about what metrics we need to actually calculate this size of, say, a slice of pizza or a portion of a circle. First thing that we're going to have in our diagram here is our central angle. Our central angle in this particular example is the measure is going to be 60 degrees, and you'll be able to see that as notated kind of the 60 inside of the portion versus saying the 300 degrees that are in the outside portion. So for our particular central angle here, it's going to be angle AOB, with O being our vertex or the center point. Next up is going to be a term called our arc measure. Or arc measure is kind of like a line segment but in a circle. Our notation is going to be that of AB. And in this particular example, we can say that our arc measure has a value of 3 pi. And the pi there is kind of specific because what we're talking about with arc measure is like the distance or length of this particular segment. And one of the ways that we can go about calculating that is through things like our circumference. So if we're going to qualitate it or define our arc measure, it's going to be a portion of a circle bound between two endpoints that lie on the physical circle itself. So we're talking about that central angle that going a radius from our center point or HK value all the way out and stretching. So it's basically dividing our circle into a portion. And the last term that we're going to have here in this particular section is going to be the sector itself. The sector is the actual slice of pizza, if you will. The sector typically is going to be notated besides just that angle that's in there that gives us an indication. It's also going to have like some type of shading. And if you're artistic and you like to have like perfection in your figures, if you will, you can always use a fingertip to kind of shade in some of your lines there. But our main focus here, what we're kind of taking away here, is that we have certain measurements that we need to qualitate our particular section or sector of our circle. That being an angle, that being something like, say, a radius or a diameter, some distance measurement going from the middle to the outside, and then some length going around. As long as we have 2 out of 3 components, we can work our way and use deductive reasoning to kind of go back and forth and find stuff. So what I'd like to do is show you examples of some different types of circles. We have what we would call, say, a semicircle. A semicircle is going to be essentially half a circle, if you will. 1/2, or we take the whole value and we divide it up by 2. Semicircle is basically just a little half portion. If we're going to go ahead and apply, say, measurements to this, theoretically, to our semicircle, we can say that the measure of angle TRJ, which in this particular example is going to be for President Teddy Roosevelt Jr., we're going to say it's 180 degrees. And if, say, diameter TJ was equal to 12, if we want to go about finding the actual circumference or the length of arc JT, we can kind of say, oh, it's half of our circumference of our original circle. So we could just do something, say, like our circumference is equal to 12 pi, our diameter times pi gives us our whole value, and then we just multiply it by 1/2. Not too bad. Pretty straightforward. If it's half the circle, it's going to be half the circumference. If it's area, it's a little bit different equation, which we'll see later on through your independent practice, but for circumference, we're just dividing by 2, essentially. We're multiplying by 1/2. If it's something like a quarter circle, which you'll see my little figure here is drawn slightly different. Occasionally what you'll see is with the circle drawn, you'll have your sector, your shaded in portion, but to notate that it was originally part of a circle, say, you'll see like dashed lines for the portions of the outlined value of the circle. For our quarter circle here, if we were to say have an angle measure here for presidential angle FDR, we can say that it's probably going to be something like 90 degrees, because it's 360 divided by 4 gives us 90, 90, 90, 90, and 90 adds up to 360. We can say, if the diameter total value was of 6, our circumference would be something like 6 pi times 1/4. So this is an easy way to break it down, but realistically not all circles, not all pies or ice cream cakes or whatever are going to be cut in these equally congruent pieces that give us nice valuable fractions that our heads are able to calculate conveniently because we've done it so many times. Occasionally you'll have like weird angles. You might have something say 60 degrees or something maybe equivalent to like 161 degrees. How do we go about qualitating that versus the number like 1/2 that we can kind of get a pretty good idea with that in our head? The way that we go about doing this is creating proportion. We've done proportions with things like our scale factor when we were taking like a triangle or a square or rectangle, and we're increasing it in size by a factor of say 2 or 1/2 or 1/3. We kind of knew the way to work with those metrics. Sectors, in a sense, are kind of like these scale factors. They're portions of our circle. So if we wanted to like convert this in a way, we basically set that degree measure up as a fraction. Since we're not working with a number out of 100, as I told you guys before, all circles, obviously 360 degrees, but we can thank our friends, the Sumerians, with their number systems that focused on the value of 6. We end up having to turn our angle into a fraction. But you might ask, what is that fraction out of? That fraction is just basically going to be a fraction out of 360 degrees. So for instance, in this particular one, we can go ahead and say, oh, this section right here, if we're looking at like the area, the circumference, is going to be something like 60 over 360. If we had an angle of 161, then it'd be 161 over 360. So this is one of the ways that we can set up our values. We can go ahead and do just fractions. The other thing that we can do is kind of set up proportion statements. Proportion statements, just to remind you, is like when we have our equivalency statements, when we had our original first leg over our our scaled up first leg equal to our second leg versus over our scaled up second leg. We want to set up some type of equivalency statement to work with all of these numbers. To show you how to do that, we have 3 different steps that we're going to look at to kind of go through this process, and hopefully the logic will kind of make it, or the step-by-step process will make it a little bit easier for you. So we're going to use that same circle again. This time we have it all labeled out. We have circle O, which is notated here, our little circle symbol, a circle with a dot in the middle, and then the letter next to the center point, our HK value. We have a radius of 12, So we have a diameter of 24. And we have radii, which is the plural of radius, of OA and OB. You can also say we have arc BA as well too. So first thing that we want to do here is find basically the original value of our circle. Once we find the original value, we can then go ahead and figure out what the proportion is, or how we relate that 60-degree measure. Now, if we take our circle of 60 degrees and we want to find our circumference, we would just do, we'd end up with 2 times our radius of 12, and we have a circumference of, say, 24 pi inches. If we're looking at our area, we would do pi times 12 squared, which would give us 144 pi inches squared. We want to remember to add this square value, this floating 2, onto our measurement specifically, not on the numbers itself, the actual measures itself. But since the area we quantitate as something that has length and width, and then eventually when we talk about cubic figures as with depth, we want to make sure that we notate this value as squared. The next portion that we have to do in terms of solving for our sector value is we need to figure out what proportion is being asked for. In this particular example, our proportion is going to be, once again, 60 over 360. This example, that's 60 over 360, is conveniently equivalent to a smaller fraction of 1 over 60. Sorry, 1 over 6. Our third and final step is we basically apply the proportion to our values. If we're going to take a look at it and talk about our circumference, our original circumference, we saw it was 24 pi, 1/6 times 24 pi gives us a final value of 4 pi inches. And if we apply that proportion of 1/6 for our area, we'll say C and A. We do 1/6 times 144 and inches, 144 pi inches squared. We end up getting a value of 24 pi inches squared. Typically, it's nice to leave your answers in terms of pi. I'm going to push you sometimes to do the whole measurement value, like the numerical value, like you saw in your JunoPod from last week or a couple weeks ago. Sometimes you'll see, like you will for today, you're going to be leaving a lot of your work in pi terms, or the terms of pi. There's another way that we can also solve this. As I mentioned before, we had equivalency statements that we can use. For our equivalency statements, we're going to have to kind of get through some of this information here oftentimes as well, but occasionally we'll be given some of the whole value data, as we can call it. When we're doing our proportional relations, what we're looking at is basically setting up as a part versus a whole. The way that gets expressed numerically, if we're going to set it up as a fraction, would be our part over our whole. If we're going to do this with the varying forms of measurements with inside of a circle, we can do our central angle over the whole angle, which is 360 degrees. The other examples that we have is our arc length, which would be BA, or arc length over our circumference, or the whole value around the circle, which is equivalent to 2 pi r, or pi times diameter. And the last portion, if we're talking about area, we'd be using the term sector. And area, we quantify the whole value as pi over r squared. So these we can set up. Occasionally, depending upon the type of question, you might have to find the arc length, but also find your whole circumference, but then you'll be given the necessary information. You'll be given the degree measure, or that central angle, which allows you to set up your original proportion, and then you might be given like your radius or your diameter, which then allows you to apply that to like the circumference or the area to get that whole bottom value. What I'd like to do before we finish up is, based on the requests from some of you, you asked me to, besides give you all hundreds and make the videos extremely shorter, is also provide you examples or some like independent practice question type stuff. What I have set up here on our paper is I have one example I came up with myself, and then I have the independent practice question number 3. So you can follow along with that as well too. In our first example here, we have circle, we'll say C. And in circle C, we have points A and B, or arc AB. What I'm going to be asking you for in this particular question is we want to find the whole circumference. So you might see this worded in different ways. You might see find the whole circumference, or your question might be presented as find the circumference of so-and-so figure or so-and-so example, basketball rim, ball, things like that, frisbee. From here, we can do a couple things. Since we're being asked to find the circumference, we're going to set up a proportion statement. For this particular one, we're going to do the value of 15, our degree measure, over 360. You can think about the left side sets up the fraction or the proportion we use. The next we're going to do is look at our circumference value, or the length it takes to go around that particular figure. For this one, we know our part is going to be equal to 3 pi. And what we're going to do is apply an x. The x value we're going to say is the circumference of the whole figure. Hey Viv. So in one thing to consider here, if we're just applying a value for x and we're saying it's the whole circumference, if we're then asked to find, what is the length of, say, CB, the radius, we can then take that value and extract out that r or that diameter. So let's just go through here. With this question, we can say we have 15x equal to 360 times 3 gives us 1080. Awesome game for Nintendo 64. We can do next divide by 15. And that gives us a value of 72 pi as our x, or our whole circumference. If we then want to go ahead and find, say, like our radius value, we can then go ahead and say, okay, so we know that in the equation for circumference, it's 2 times the radius times pi. That means we can then go ahead, divide 72 by 2. That leaves us with pi r, or 72 equal to r. So we have our pi as pi. The last thing I want to show you here is going to be example for number 3 in your independent practice. What you'll see on your paper that you're going to complete and hand in for your IP today is question number 3's got a semicircle, or sorry, a portion of a circle. It's 270 degrees. You'll see the 270 is going to be labeled on the exterior portion or in the shaded area itself, which kind of gives away what portion we're looking at of the figure. So I'm going to show you 2 different ways to go about this. The first one's going to be our proportion statement. Since we're talking about the area, we're going to set up our proportion side 270 over 360. X is going to be our part area. Your whole area, we have to go ahead and calculate, similar to our previous notes page. Our area formula, as we know, is pi times r squared. So r squared being 3 squared, we have 9 pi. 2 minutes. The last thing that we have to do is essentially cross multiply, and then we are able to finish up with our question. We do 270 times 9 pi, we get a value of 2430 pi equal to 360. We divide out our 360 and we get 6.75 pi equal to our x. The other way that you can do this, 270 over 360 is equivalent to 0.75, or 3 over 4. We multiply that value times 9 pi and we get 6.75 pi as well. For your assignments today, you'll see that there are 3 different portions. You have an Edpuzzle listed, a independent practice, an exit ticket, and a what I would like for you to do today is, with your assignment, your independent practice, I would like for you to upload to the independent practice section so I can give you an assignment grade for completing it. The questions that are listed there, I've kind of decided to give and distribute you information in a different way. Your independent practices are going to be easier. Your exit ticket questions probably going to be like a medium, and then you'll have homework questions, which are going to be kind of medium and hard, to kind of push you to contextualize this information or apply additional steps of logic. You're still going to have the same amount of content that you normally have been having, but as opposed to making you do like 15 or 20 questions within one day, and plus watch your Edpuzzles, give you the opportunity to kind of do some of that harder material and hand it in our next class assignment. So you'll see a homework section. Please make sure to pop that in there by Thursday morning. For your exit ticket, what I would like for you to do is just once you complete, there's a file, you can go through, answer it, show your work and all that. I want you to upload your work to our Google Classroom. So I have a copy of it, and I can see your work and check your mistakes and things like that and help correct everything for you. I also want you to go into Jupyter and input your answer. That way you can check to see if you're right, essentially right away. So the JunoPod is just really simple. You're just going to put your answer in there, and that's it. It should take you 30 seconds to do, but please make sure to upload your exit ticket. If you have any questions, by the way, please make sure to hop into office hours. We're always there answering a bunch of questions for independent practice. Normally we finish, if not 100% of the questions, somewhere around 75%. So you can get a lot of stuff done between that time, hang out, talk about music, all that fun stuff. So if you have questions, please message me, email me, but office hours is always the best. All right. Have a nice day.